Signals and Systems, CT Fourier Transforms, Series on Signals and Systems, Lecture number 3.11. Signals are meant for carrying information from one point to another point. They are characterized by the capability of carrying information. This capability depends upon their frequency content. When the signal is in time domain, it is difficult to know or to see the frequency content of the signal, and hence it is not possible to estimate its capability in carrying the information from one point to another point. To know the frequency content of the signal, it has to be transformed into another domain, that is frequency domain. Several techniques are there to transform signal from time domain to frequency domain, and some are applicable for periodic signals and some are applicable for non-periodic signals, and some are useful when there is a loss in the signal transmission. Right now, here in the present session, our focus is on one particular transform called CT Fourier Transform. This transform is useful in converting a continuous time non-periodic signal into frequency domain. With this small brief to the present session, now let us move further to understand the basics, the definition, and the importance of Fourier transforms in signals and systems subject. We begin the session with the definition of Fourier transform. Here it is CT Fourier transform. CT stands for continuous time Fourier transform. DT Fourier transform is also there, and that is applicable or useful for discrete time signals. The present session is about CT Fourier transform. Here the definition of Fourier transform is given. The Fourier transform f of omega. Omega stands for angular frequency. For a CT non-periodic signal, f of t is defined as. So f of omega is Fourier transform, f of t is signal. F of t is signal in time domain, f of omega is signal in frequency domain. F of omega is equal to integral minus infinity to plus infinity f of t e power minus j omega t dt. This equation, it is called analysis equation. This equation helps us converting time domain signal into frequency domain signal. It is also called forward transform. Now let us come to the second equation, which is called synthesis equation. F of t is equal to 1 by 2 pi integral minus infinity to plus infinity f of omega e power j omega t t omega. We can see it converts frequency domain signal into time domain. It is called reverse transform. The frequency domain signal f of omega is in general a complex function. It's a complex quantity depending upon angular frequency omega. It is called spectral density function. The name of f of omega is spectral density function. Now let us move to another aspect of CT Fourier transforms. It is Dirichlet's conditions. What are Dirichlet's conditions? It has been told that CT Fourier transform, it is meant for continuous time non-periodic signals. But the fact is, not all continuous time non-periodic signals can have CT Fourier transforms. Only certain CT non-periodic signals can have Fourier transform. In fact, only those which satisfy Dirichlet's conditions, they only can have CT Fourier transform. What are these Dirichlet's conditions? For the existence and convergence of a Fourier transform to a signal f of t, 1. F of t should be absolutely integrable. That is, integral minus infinity to plus infinity, magnitude f of t dt should be less than infinity or finite. If this condition is satisfied, we see that integral on the right hand side of the equation. This is the defining relation of Fourier transform. F of omega equal to minus integral minus infinity to plus infinity f of t e power minus j omega t dt. It is guaranteed to have a finite value. What he is telling is, if f of t satisfies this relation, then right hand side of this equation, it means this integral, it then is finite. Otherwise, it is infinite. When it is finite, then only f of omega carries meaning. Second point, f of t must have only finite number of finite discontinuities within any finite interval. Third point says f of t must contain only finite number of maxima and minima within any finite interval. According to the second point, discontinuities can be there in the function, but they must be finite. Third point says number of maxima and minima within a finite time interval must be finite in number. After going through all these three statements, one can notice the similarity between Dirichlet conditions meant for Fourier transforms and Dirichlet conditions meant for Fourier series. One can notice a very little difference between these two sets of conditions. Although the Dirichlet conditions are sufficient for the existence and pointwise convergence of the Fourier transform, they are not necessary. It implies there are signals, even though they do not satisfy Dirichlet conditions, they have Fourier transforms. Now let us move further. Energy. Signal usually refers to either voltage or current. Sometimes it may refer even to a field, electric field or magnetic field. Voltage, current, they are associated with power and energy. Power is more relevant to periodic waveforms, whereas energy is relevant to non-periodic waveforms. We are in CT Fourier transforms. which are meant for non-periodic signals. Therefore, in the present context, energy is a more relevant quantity as far as signal is concerned than power. We spent some time on understanding energy within a non-periodic signal in the present slide. We first define a quantity, energy density. It is indicated by S of omega. It is, by definition, the energy per unit bandwidth. It can be shown S of omega is equal to 1 by pi absolute value of f of omega or magnitude of f of omega square, this relation. There is a theorem called Rayleigh's theorem. This theorem is about energy of a non-periodic signal. What this theorem says, the energy of a non-periodic signal f of t is equal to 1 by 2 pi times the area under the f of omega whole square curve. Mathematically, E is equal to integral minus infinity to plus infinity f square of t dt. It is equal to 1 by 2 pi integral minus infinity to plus infinity f of omega whole square d omega. This is basic definition of energy. With a little manipulation, one can show that it is equal to 1 by 2 pi integral f of omega whole square d omega integration from minus infinity to plus infinity. Of course, from this relation, energy can be expressed in terms of energy density function as E equal to integral 0 to infinity S of omega d omega. To move further, it has been mentioned in the beginning that Fourier transforms, they are meant for non-periodic signals. But one can see after moving a little bit deep into the theory of Fourier transforms that the Fourier transform can be obtained. It can be found even for periodic signals with the help of Dirac delta function or impulse function. Let us spend some time on discussing about this particular topic. The Fourier transform of a periodic signal consists of impulses located at the harmonic frequencies of the signal, and that the strength of each impulse is the same as 2 pi times the value of the corresponding quotients in the exponential Fourier series. So this is the statement. After the statement, he is giving some mathematical proof too. Consider the exponential Fourier series expansion of a periodic function. This is exponential Fourier series expansion. Now he is applying Fourier transform on both sides. The Fourier transform of f of n e power jn omega naught t. It is equal to 2 pi times sigma minus infinity to plus infinity fn delta omega minus n omega naught. Here he used, in deriving this relation, he used the connecting relation, Fourier transform relation between exponential function and delta function, about which we are going to see soon in the present session itself. Now, IFS means infinite Fourier series to CTET. The connection between infinite Fourier series and CTET. There exists a connection. That particular relation, connecting relation, it is explored here in the present slide. As the time period t tends to infinity, the periodic signal becomes a non-periodic, and analytically, three changes can be noticed. What are those three changes? N omega naught becomes omega. N omega naught in infinite Fourier series expansion, it becomes omega. Fn t, Fn is exponential Fourier series quotient, t is time period. The product of these two, they become f of omega. And sigma, which is a symbol for addition, it becomes integration. Now, keeping these three changes in mind, one can say f of t is equal to sigma minus infinity to plus infinity fn e power jn omega naught t. This is Fourier series expansion, of course. It becomes, as t tends to infinity, it becomes 1 by 2 pi integral minus infinity to plus infinity f of omega e power j omega t d omega. Now, Fn, exponential Fourier series quotient. Fn is 1 by t integral t f of t e power minus jn omega naught t dt. It gets transformed into f of omega equal to integral minus infinity to plus infinity f of t e power minus j omega t. So this is a forward relation, this is a reverse relation. Fourier transforms, they exhibit certain properties. All those properties are listed. These are useful for us when we go deep into the subject, as well as when we apply the transforms to the practical or real-time situations. Those properties are one after another we consider here. First one is linearity. This property says A f1 of t plus B f2 of t. It gives a Fourier transform, which is A f1 of omega plus B f2 of omega. Notice f1 of omega is Fourier transform of f1 of t. f2 of omega is Fourier transform of f2 of t. A and B are constants. So the linearity property, it is mentioned through this mathematical relation. Duality relation, duality property. It says capital F of t gives a Fourier transform which is equal to 2 pi small f of minus omega. Notice small f refers to time domain signal, capital F refers to frequency domain signal. So in place of omega, in f of omega, capital F of omega, if we substitute t, then we will be getting capital F of t. Its Fourier transform then becomes 2 pi times small f of minus omega. How can we obtain small f of minus omega? In place of t in the time domain signal, place minus omega. So this relation is known as duality property. Next, conjugation symmetry. Conjugate of f of t. F of t is the signal. The star here indicates conjugate. You consider conjugate of the f of t. For the conjugate of f of t, the Fourier transform is conjugate of Fourier transform of f of t with minus omega in place of omega. This property allows us to show that if f of t is real, that is f conjugate of t equal to f of t, then f of omega has conjugate symmetry, that is capital F of minus omega is equal to F conjugate of omega. Now we move to another property called time scaling. F of AT, its transform is 1 by A capital F of omega by A. This is called time scaling property. It implies for a positive A, here A is constant, when it is positive, F of AT, its transform is 1 by A capital F of omega by A, and F of minus AT, its transform is 1 by A F of minus omega by A. This property states that compression in time domain is equivalent to expansion in frequency domain and vice versa. For A equal to minus 1, we get the following relation. Time reversal. When A equal to minus 1, the resultant property is called time reversal property. According to this property, F of minus t gives a Fourier transform F of minus omega. Now move to another property, time shifting property. F of t minus t naught, its Fourier transform is F of omega multiplied by e power minus j omega t naught. This theorem states that if a function is shifted in time domain by t naught seconds, then its magnitude spectrum remains unchanged, but phase spectrum changes by an amount minus omega t naught. Another property is frequency shifting property. F of t e power j omega naught t, its Fourier transform is F of omega minus omega naught. This theorem is also known as frequency translation theorem. It states that a shift of omega naught in frequency domain is equivalent to multiplication by e power j omega naught t in time domain. It is a dual of time shift theorem, which we considered under 6. 6 is a time shifting theorem, 7 is frequency shifting. Now, let us move further to consider time differentiation. The Fourier transform of f of t differentiated n times dn f of t by dtn. Its Fourier transform is j omega power n multiplied by f of omega. The time differentiation theorem states that differentiation in time domain is equivalent to multiplication by j omega in frequency domain. It is useful in deriving the Fourier transform of sum of continuous functions. Another property, frequency differentiation. Minus jt power n f of t, its Fourier transform is d power n f of omega by d omega power n. This theorem states that differentiation in frequency domain is equivalent to multiplication by minus jt in time domain. Another property, time integration. The Fourier transform of integral minus infinity to t f of tau d tau is 1 by j omega f of omega plus pi delta omega. The time integration theorem states that integration in time domain is equivalent to division by j omega in frequency. Some more properties. Frequency integration. This property says Fourier transform of 1 by minus jt f of t is integral f of omega t omega. The frequency integration theorem, this relation states that integration in frequency domain is equivalent to division by minus jt in the time domain. Another property, time convolution. f1 of t convolution with f2 of t. The Fourier transform of the resultant signal is equal to f1 of omega multiplied by f2 of omega. In time domain, it is convolution. In frequency domain, it is just multiplication. The time convolution theorem states that convolution in time domain is equivalent to multiplication in frequency domain. To move further, we consider frequency convolution. The Fourier transform of product of two signals f1 of t multiplied by f2 of t, it is equal to 1 by 2 pi f1 of omega convolves with f2 of omega. So one can notice the frequency convolution theorem or property states that multiplication in time domain is equivalent to convolution in frequency domain. So far, we covered important properties of Fourier transforms. They are more than 10. They are highly useful when we start using them. Now, we consider certain transform pairs. Under transform pairs, we consider a signal in time domain and its corresponding frequency domain. Around 18 pairs are given. Let us start from the beginning. Fourier transform of delta t is 1. Delta means Dirac delta function or impulse function, single impulse here. Fourier transform of 1 is 2 pi delta omega. In 3, an impulse train is considered, delta t of t, impulse train. For this, Fourier transform is omega naught delta omega naught of omega. 4 is about Fourier transform of an exponential function e power j omega naught t. For this, Fourier transform is 2 pi delta omega minus omega naught. 5. Here, Fourier transform of cos omega naught t is given. It is in terms of impulse functions, two impulses, one at minus omega naught, another at plus omega naught. In 6 is sin omega naught t. For this, Fourier transform is j pi delta omega plus omega naught minus delta omega minus omega naught. In 7 is given Fourier transform of unit step. It is equal to 1 by j omega plus pi delta omega. In 8 is given a gate function. Gate function is rectangular pulse with tau. For this, Fourier transform is tau sampling function omega tau by 2. In 9 is given Fourier transform of a sampling function. Notice for gate function, Fourier transform is sampling function, and for sampling function, Fourier transform is gate function. In 10 is e power minus at. For this, transform is given as 1 by j omega plus a. In 11, t e power minus at u of t. For this, Fourier transform is given as 1 by j omega plus a whole square. In 12, e power minus a t. For this, transform is given. In 13, a triangular function is considered Fourier transform. For this triangular function, it is found as sampling function square. In 14, sampling function square is considered in time domain and its Fourier transform is found to be a triangular. So triangular function gives sampling function square in frequency domain Fourier transform, whereas sampling square time domain signal gives triangular function in frequency domain. In 15, the Fourier transform of signum function is given. It is 2 by j omega. In 16, Fourier transform of 1 by t is considered. It is minus j by signum omega. In 17, Fourier transform of differential of impulse function is considered. Is j omega power n. In 18, Fourier transform of t power n is considered. It is 2 pi j power n d n delta omega by d omega. Now let us review the aspects of Fourier transforms that are considered in the session. We started the session with defining relations of Fourier transform and inverse Fourier transform, and then Dirichlet's condition, and then various properties of Fourier transforms, and different commonly used Fourier transform pairs are considered. Now we come to the closure of the session. Hope this session is useful to you. We meet again in another session soon with another new topic.